Our topic for today is 11.4D Thermodynamics. This is the last podcast for grade 11 Cambridge Chemistry. The assessment criteria is as follows. You should be able to know how to calculate delta H from bond enthalpies. You should be able to construct a Born-Haber cycle for ionic compounds and compare the lattice energies using this approach. You should be able to know and define the concepts that make up free energy. You should be able to use the Gibbs free energy equation, and you should be able to understand that enthalpy change alone is not sufficient to explain spontaneous changes and recognize the role of entropy in thermodynamics. So, calculation of delta H from bond enthalpies. We have seen this one before. We saw this one when we talked about reactions earlier this year. And the delta H of a reaction is the sum of the delta H's of the products minus the sum of the delta H's of the reactants. Here you can see methane and oxygen making carbon dioxide and water. To determine the delta H's of the products, we would have to determine how many bonds exist in the products. In CO2, there are 2 carbon-oxygen double bonds. So that would be 2 times 799. How about H2O? In H2O, you have 2 oxygen-hydrogen connections. That is 2 times 459. But you have 2 molecules of this, so it's 2 times 2 times 459. Doing the same for the reactants, we could then find out the delta H of the reaction by subtracting the delta H of the reactants from the delta H of the products. Let's take a look at a Born-Haber cycle. This is, if you look at the left-hand picture, the formation of a salt from perhaps a group 1 element and a halogen. It could be sodium and it could be chlorine. You'll notice that there are steps where energy is used to change that solid to a gas and then to ionize that gas. You can then see, if you look at the halogen, you have to be able to dissociate that halogen and then have it accept an electron. These energies are able to be added and subtracted. And so if you look on the right-hand side, you'll see an example done for you for sodium mixing with chlorine gas to give NaCl as a solid. We're looking to find the lattice energy, and that lattice energy can be found by the formula. You'll see the direction of the arrows. The direction of the arrows is arbitrary. Normally, going down is plus and going up is negative. Take a look at this Born-Haber cycle and pause the tape. We'll be back to you in a minute. It says you should be able to define and use the concepts of free energy change, delta G and delta S. Free energy is a competition between the change in enthalpy, the making and breaking of bonds, and the entropy as the temperature increases or decreases. The result of this competition between delta H, the temperature, and entropy is called Gibbs free energy. And it will give us an indication of whether a reaction happens by itself or needs assistance, spontaneous or non-spontaneous.
I'm going to try to tackle something that's been a problem for years. I'm going to try to make Gibbs free energy more understandable, and so that you really know what it is and understand the power of it, especially in biology. And so I think the first place to start is the name itself. The idea of free kind of gets in the way. And so what I'd like to go back to is the old name, which it used to be called available energy. And so let's think of delta G as available energy, or energy that we can actually use to do work. The other thing that I think makes it hard is the equation itself is confusing. We've got delta G, we've got enthalpy, we've got entropy, we've got words that you're maybe not understanding. And so what I'm going to try to do is pare this down to the easiest explanation that I can, and then we can get into the more of the specifics a little bit later. And so the best place to start when you're trying to understand available energy or free energy is to look at spontaneous reactions. Spontaneous reactions are reactions that once you give them a little bit of a push, they'll actually go on their own. These reactions also will tend to release energy, and they give energy to their surroundings. Quintessential example in life is cellular respiration. But let's not get there yet. So the three reactions that I'm going to talk about here are, number one, a ball rolling down a slide. Number two, diffusion. And then number three, a cherry bomb that's exploding. And so we're going to apply Gibbs free energy to each of these. So let's start with the ball at the top of the slide. And the ball at the top of the slide is going to roll down to the bottom. And so the first thing that I want to give you is what's called enthalpy, or total energy of a system. And so if we say this is a system, what happens to the total energy of the system as the ball rolls down the slide? Well, if you know anything about potential energy, the amount of potential energy that we have up here is going to be greater than the amount of potential energy that we have down here. And so the total energy of the system, we'll call that H, or enthalpy. The total energy of the system has gone from a big H to a little h. In other words, the total energy of the system has decreased when the ball rolls down. Now, if I had to push it up again, then we would add energy to the system. But this is a spontaneous reaction, and the enthalpy, or the total energy, is decreasing. Now, in biology, we don't move around because of potential energy or mechanical potential energy. In biology, our energy, or our potential energy, is actually in these bonds. In other words, there's a huge amount of potential energy in this bond between the carbon and the hydrogen. And so this right here is glucose. And if we can release some of that energy, we can do it to do work. And so again, what is H? H stands for the total energy of the system. And it looks like in a spontaneous reaction, that's actually going to get smaller or decrease. Okay, next one, let's talk about diffusion. So in diffusion, imagine that right here we've got a bunch of molecules in this container and they're bouncing around, and I remove this wall. So if I remove that wall, what's going to happen to the molecules? The molecules are going to spread out to fill that area. We call that diffusion. Now entropy is, we use the symbol S for that. Entropy is a measure of the disorder of a system, or sometimes we call that the randomness of the system. And so let's compare this. Right here we've got a bunch of molecules on this side, and then we got a lot of space over here. So what happens to the disorder of that system as I do diffusion? Well, it's becoming more disordered. In other words, the entropy is increasing. What's an example of that? Let's say I go into your room and your room's a mess. It looks like this. If I say clean up your room, then you could go like that. And so what happens through diffusion, or in this spontaneous reaction? Well, let's say remove this wall. What's going to happen now? We're going to get even more disorder. So we're going to even get a bigger S value. And so in this spontaneous reaction, it looks like the S value is increasing. Okay, the last one is that cherry bomb. So let's say we have a cherry bomb, we put it on the desk. Does it explode? No. And one of the reasons it doesn't is the temperature is really low. And so let's say I add a bonfire to the situation, so I increase the temperature. Does that make it a more spontaneous reaction, or is the reaction more likely to happen or less? Well, it's more likely to happen if I increase the temperature, more likely to get an explosion. Okay, so those three things, total energy or enthalpy, entropy or S, and temperature can affect spontaneous reactions. And so now let's apply that to Gibbs free energy. And so before we actually get to the equation, let's just do a little algebra here. So let's say I wrote this equation, x equals y minus ab. Okay, so let's say we had this equation right here, and I were to decrease this value, the y value. What would that do to the x value? It would decrease it, right? Let's say I were to increase the a value and increase the b value. What would that do to the x value? Well, since we're subtracting right here, that would decrease it as well, or make it even go farther down. And so let's go back and summarize those three spontaneous reactions. In the first one, the ball rolled down. So what happened to our H value? Well, our enthalpy of the system decreased. What should that do to our Gibbs free energy or available energy? It should decrease that value. What happened here when we increase the entropy of the system or increase the delta S? Well, if we increase the delta S, that should also decrease the Gibbs free energy. So now we have two things decreasing that. And what happened here? Well, if we increase the temperature, that made it more spontaneous. So if we increase that, we also decrease the Gibbs free energy. So what's the moral of the story? Moral of the story is that if the delta G ever decreases, or if it's ever less than 0, that's a spontaneous reaction.
Here's an example of using the Gibbs free energy equation. You'll notice that what is given to you are the delta H, the enthalpies of the reaction, the amount of entropy, and the temperature. The value of delta G can be calculated using delta G equals delta H minus T delta S. Now, given any three of the four, you should be able to calculate the missing value. Enthalpy change alone is not sufficient to explain spontaneous changes. You saw in the last slide the effect that temperature and entropy has. So you have a set of choices that can happen when delta H is bigger than 0 or when it's less than 0. When delta S is bigger than 0 and when delta S is less than 0. If delta H and T delta S are equivalent, then the reaction is said to be in a state of equilibrium. Here are two ways of looking at and determining whether a reaction is spontaneous or non-spontaneous.
A hot and messy reaction will always be spontaneous. By hot, I mean exothermic, delta H is negative. And messy, I mean the entropy is increasing, delta S is positive. So hot and messy reactions will always be spontaneous, delta G will be negative. Cold and tidy, these reactions will never happen. Cold is endothermic, delta H is plus. And tidy, well, delta S, the entropy change, is negative. These reactions will never happen. So, to recap, hot and messy always happens. I know this sounds weird, but if I remember it like this, I find the delta G equation easier to understand. Hot and messy always happens. Delta G is negative, spontaneous. Cold and tidy, that never happens. Cold is endothermic, and tidy, well, delta S is going to be negative, entropy is decreasing. Delta G is positive. It's non-spontaneous. So the interesting part is, what if it's a different combination of those two? For example, if it's hot and tidy, does it happen? Or if it's cold and messy, does the reaction happen? Well, those reactions are temperature dependent, and that's what this unit's about. Well, for this reaction that's used to make iron, delta G, when it's plus, it's non-spontaneous, that's always the case, and negative delta G is spontaneous. Now, looking at the equation, you couldn't tell that delta H is plus, I'd have to tell you that. But delta S is plus, entropy is increasing. Yeah, you could work that out, because a gas is produced from solids. So don't forget, delta H is plus, it's endothermic, or it's cold, and delta S is plus, it's messy. So this is temperature dependent, this one, cold and messy. So delta G depends on the temperature. So allow me to sketch in the graph, as temperature increases, the effect on delta G. Well, it should be clear that as temperature goes up, delta G goes down. And at this point here, well, that's important. There, delta G is 0, and it's about to become spontaneous at delta G equals 0. It's also equilibrium, but the IB doesn't need you to know that. That's 840 Kelvin. So that's the magic temperature. 840 Kelvin, this reaction will actually start. And as you increase the temperature further, delta G becomes more and more negative.
Here are some questions to start your thinking. How can you use Gibbs free energy equation to determine the temperature range at which a reaction may be spontaneous if you're given delta H, delta G, and delta S? Gibbs free energy is a measure of what, and entropy is a measure of randomness. How do the states of matter, gas, liquid, solid, represent changes in randomness?